The quiet night sky is the remnant of a single point. Rewinding 13.8 billion years collapses every star and galaxy into a searing, high-density speck. Every piece of matter and every inch of space we observe originated from this explosive singularity. However, mapping the deep cosmos reveals a physical contradiction. Regions of space separated by billions of light-years share the exact same temperature, though they are too far apart to have ever exchanged heat. The geometry of the universe is also perfectly balanced. A density deviation of even 1 part in 10 to the 62nd power at the beginning would have caused the cosmos to either collapse inward or fly apart before the first stars could form. This consistency suggests regions now separated by the entire sky were once in direct contact, requiring a process that unified temperature and smoothed the shape of space at the very start. Physicists address these contradictions with the theory of cosmic inflation. In a fraction of a second, space itself expanded exponentially, growing faster than light speed. Rapidly stretching space pulled initial geometric curves tight. Like a massive balloon, reality expanded until it appeared perfectly flat. This expansion pushed once-touching particles to opposite ends of the visible sky, locking in their identical temperatures. Space itself stretched and multiplied. New distance opened up between particles, driving them apart as the fabric of the universe expanded. Inflation ironed out physical irregularities of the early cosmos. It created the smooth, uniform stage required for the laws of physics to begin their work. When this expansion ended, the energy behind it transformed into matter. The universe became a 10 billion-degree primordial soup of fundamental subatomic particles. To understand this era, physicists use massive particle accelerators to recreate these conditions. By smashing particles together at near light speed, we can observe how matter behaves at these extreme temperatures. These experiments map the era of Big Bang nucleosynthesis, a window of time occurring within the first 3 minutes of creation. Extreme pressure forced protons and neutrons to collide and bond. In this brief window, the very first atomic nuclei began to form. The output was almost entirely hydrogen and helium, with only a microscopic trace of lithium. The heat was still too intense for heavier elements to survive. As the universe cooled, this 3-minute window of fusion ended. It locked in the elemental ratios of the cosmos, providing the raw materials for every future star and galaxy. For the next 380,000 years, the universe existed as a glowing orange haze of superheated plasma. In this environment, electrons were stripped from their nuclei. They moved freely through space at high speeds, creating a dense barrier of charged particles. This plasma blocked the movement of light. A photon attempting to travel forward instantly ricochets off a free electron. Across the cosmos, light was trapped in this continuous ricochet. The photons were present but could not escape the plasma. The universe was filled with energy, yet it remained opaque. This trapped light made it impossible for any observer to see through the haze. This physical barrier lasted for nearly 400,000 years. Because the light was imprisoned in plasma, the exact moment of the Big Bang remains hidden from our telescopes. As space continued to expand, the particles lost their kinetic energy. The glowing orange sea cooled, allowing particles to slow down and form orderly bonds. The temperature of the universe dropped until it hit 3,000 Kelvin. At this threshold, electrons locked into orbit around protons, forming the first neutral hydrogen atoms. This event is known as recombination. With the electrons now contained within atoms, the cosmic fog cleared. The trapped photons were suddenly free to fly straight across the vacuum. We have successfully mapped this first flash of liberated light. It is the cosmic microwave background, an ancient signal captured by specialized satellites like WMAP. The cosmic microwave background serves as a physical fossil. It is a snapshot of the exact moment the universe transitioned from a chaotic plasma into a transparent void. Expansion eventually stretched this first light, shifting its wavelengths from glowing orange into the invisible microwave spectrum. The universe then entered the cosmic dark ages. For 200 million years, the cosmos was a cold ocean of transparent hydrogen gas, with no stars to light it. Gravity began to organize this gas, pulling matter into dense, spinning nodes within the darkness. During this invisible era, gravitational forces pulled primordial hydrogen together to form the first large-scale structures. Modern astronomy is now focused on seeing the end of this dark period. Instruments like the James Webb Space Telescope use massive gold mirrors to capture the faint light of the first structures emerging from the void. The cold darkness of the early cosmos was a period of active incubation. It provided the time and the gravity required to prepare the universe for the ignition of the very first stars. Following the Big Bang, the universe was dark. There were no stars, no galaxies, and no sources of visible light. The early cosmos was filled with a thick fog of neutral hydrogen gas. This material was opaque to electromagnetic radiation, meaning any stray photons were immediately absorbed by the dense atomic haze. But gravity was already at work. Across immense distances, it began pulling these hydrogen clouds, some stretching 100 light-years across, into a series of swirling filamentary webs. These webs held vast amounts of potential energy, yet the universe remained in this non-luminous state. Without a trigger to release that energy, the gas stayed dark and the temperature remained just above absolute zero. Over millions of years, those vast webs of gas began to fragment. They collapsed inward, condensing into dense, localized knots of matter. This diagram illustrates the physical conversion happening inside one of those knots. As the gas compresses, its gravitational potential energy is converted directly into intense heat. The resulting object is a protostar, a rotating ball of superhot gas, but not yet a true star. Deep within its core, the pressure builds. The internal temperature climbs until it approaches a critical physical threshold of 10 million Kelvin. If the core falls short of that temperature, the object remains a brown dwarf, a hot, dark sphere that slowly fades. If it crosses that threshold, the outward collapse stops and the object enters its first stage of nuclear burning. At 10 million Kelvin, the proton-proton chain reaction begins. Hydrogen atoms fuse to form helium, releasing a massive outpouring of nuclear energy. The first stars are born. These early stars were giants, possessing 30 to 300 times the mass of our modern sun, and burning with a ferocious intensity. This macro visualization shows the effect these stars had on their environment. The immense ultraviolet radiation they produced began stripping electrons from the neutral hydrogen gas that filled the early universe. This process is known as reionization. By ionizing the surrounding hydrogen, these stars physically altered the medium of space, making it transparent to visible light for the first time. Observationally, a star is an ongoing nuclear explosion, yet it does not immediately detonate like a bomb, nor does it collapse into a black hole under its own weight. This diagram demonstrates the reason, a state called hydrostatic equilibrium. On one side is gravity. The crushing weight of the star's own mass relentlessly attempts to compress the core down to a single point. Pushing back is the radiation pressure. The energy generated by fusion in the core forces the outer layers away from the center. As long as these two opposing physical forces maintain this precise balance, the star remains stable. A star is not a static object. It is a violent physical battle locked in a temporary truce. Once a star achieves hydrostatic equilibrium and clears its surrounding fog, it enters a stable phase known as the main sequence. This is the Hertzsprung-Russell diagram. Mapping temperature against luminosity shows mass dictates a star's lifespan. Upper left, massive O-type blue giants die in millions of years. Middle, mid-sized yellow dwarfs like our sun last 10 billion years. Bottom right, low-mass red dwarfs burn for trillions. The amount of matter a collapsing cloud gathers at its birth seals its fate before the first spark of fusion even begins. Every point of light in the night sky is an active engine of equilibrium, running on these same principles. This stable, long-term fusion process is what forges heavier atomic elements and provides the consistent energy output required for complex chemical reactions to persist. This balance provides the billions of years of stable energy required for planetary systems to take shape and for life's necessary conditions to emerge. 13.8 billion years ago, the universe cooled enough to allow matter to form, but that matter was overwhelmingly simple. It was almost entirely hydrogen, with a bit of helium and a tiny trace of lithium. Looking at this minimalist periodic table, only the first 3 slots are initially filled. Biology and planetary geology require much more complex building blocks, like carbon, oxygen, and iron. Those heavier elements had to be forged somewhere else. To find the origin of those missing elements, we have to look inside the universe's most extreme pressure cookers. Spacecraft like the Parker Solar Probe fly directly into the outer atmosphere of stars to help us understand how these violent nuclear engines actually operate. This graphic shows the basic mechanics of a star. It is a system locked in permanent tension. Immense gravity continuously tries to crush the star's mass inward, while the intense heat and energy of nuclear fusion at the core push outward. Every star exists as a billion-year stalemate, a violent, constant war between a massive body and its own internal engines. The engine keeping gravity at bay depends entirely on the star's size. Low-mass stars, like our Sun, convert hydrogen to helium using the proton-proton chain, a slow, steady reaction that can burn for over 10 billion years. These 2 charts contrast that process with a much more aggressive engine. Massive stars utilize the CNO cycle to maintain equilibrium. This reaction burns through nuclear fuel exponentially faster, exhausting massive reserves in just a few million years. Because hydrogen fuel is finite, gravity acts as a cosmic ticking clock. Eventually, every star runs out of its primary fuel source, forcing a crisis. When the core's hydrogen is finally exhausted, the outward pressure from fusion instantly drops. With nothing pushing back, gravity aggressively crushes the core inward. This rapid compression causes the core's temperature to spike dramatically. The sudden heat ignites a fresh shell of unused hydrogen sitting just outside the core, causing the outer layers to bloat outward and creating a massive red giant. This schematic illustrates the next phase of the reaction. The crushed core becomes so intensely hot that it forces 3 separate helium nuclei to fuse together, forging a single, heavier carbon nucleus. This is the triple alpha process. For mid-sized stars like our Sun, the thermodynamic escalation hits a permanent wall right here. The core simply cannot generate enough heat to fuse elements heavier than carbon and oxygen. The star's massive expansion into a red giant is a temporary survival mechanism. It delays gravity's inevitable victory, but it cannot prevent it. Stars with more than 8 times the mass of our Sun experience a much different fate. Their extreme mass allows the escalation to continue violently past carbon. Astrophysicists call this the stellar onion. Massive stars build concentric fusion shells of heavier elements. Hydrogen burns on the outer edge, while oxygen, neon, and silicon ignite deeper. Each successive element burns exponentially faster. The innermost silicon layer burns out in mere days. This rapid sequence leads to an ultimate atomic dead end: iron. Fusing iron breaks the rules. Instead of releasing energy, the reaction completely absorbs it. Iron is a fatal trap. The moment the core turns to iron, outward fusion pressure flatlines. Millions of years of equilibrium are broken in an instant. Once that iron core exceeds roughly 1.4 solar masses, a threshold known as the Chandrasekhar limit, it can no longer support its own weight. It collapses inward at a fraction of the speed of light. The dense core violently collapses, instantly rebounds, and triggers a catastrophic, blinding outward shockwave. This explosion involves a massive surge of elusive subatomic particles called neutrinos. We use immense detectors to track them on Earth, but inside a supernova, they supercharge the shockwave. This immense flood of neutrinos provides the energy transfer required to blast the star completely apart. The extreme violence of the explosion forces atoms together in a process called rapid neutron capture. In mere seconds, it successfully forges the heaviest elements in the universe, like gold and uranium. The explosive death of a massive star is the only forge in the universe violent enough to create heavy elements, necessary for complex planetary bodies. When the cosmic dust of the explosion clears, gravity's ultimate victory leaves behind bizarre, extreme physical remnants. We use advanced tools like the James Webb Space Telescope to peer through the gas and uncover them. Mid-sized stars leave behind white dwarfs. intensely dense, Earth-sized cores supported entirely by the quantum mechanical pressure of electrons resisting compression. Larger stars leave neutron stars, or pulsars. These are city-sized objects spinning hundreds of times a second, where the pressure is so intense that protons and electrons are literally crushed together into pure neutrons. And the most massive stars experience the ultimate fate. Their original mass was so high that gravity punctures a hole in space-time itself, creating a black hole. These extreme objects are the ultimate cosmic gravestones. They are final, immutable monuments to gravity's absolute triumph over the star's nuclear engine. Beyond the dense remnants, the expelled gas and newly forged elements now drift through the vast interstellar medium, space we are just beginning to physically explore with probes like Voyager. This slow-motion spray of heavy elements is the ultimate cosmic recycling mechanism. It provides the exact raw materials needed for future planetary systems. The explosive deaths of these atomic alchemists drive the essential recycling engine of the universe, the process that makes Earth, its atmosphere, and our own biology possible. Deep inside a collapsing molecular cloud, gravity pulls gas and dust into a dense core until nuclear fusion ignites. The result is a protostar, surrounded by a chaotic, spinning halo of leftover material. For decades, astronomers relied on a concept called the nebular hypothesis to explain what happens next. It proposes that a star and its orbiting planets co-form from this exact same collapsing cloud. According to this model, planetary formation is a highly ordered mechanical progression. Dust grains stick together, gravity slowly pulls them into larger clumps, and over time, a stable, mature system emerges. But as astrophysicists run the physical data through modern computer simulations, the math refuses to cooperate. When you attempt to build a planet using our accepted models, the process breaks down entirely. Turning a cloud of debris into a solar system requires matter to survive a gauntlet of physical barriers and strict time limits. And multiple stages, the mechanics dictate that planetary growth should simply stop. If the laws of physics operated strictly according to baseline models, the assembly line would stall. Our solar system, and the Earth within it, should not exist. The first physical barrier appears at the microscopic level. Within the swirling protoplanetary disk, millimeter-sized dust grains constantly collide. To build a planet, these tiny grains need to clump together. Instead, when they reach the size of small pebbles, their collision velocities increase. Rather than sticking, they bounce off one another or shatter entirely. This is known as the planetesimal bottleneck. Somehow, the raw material of the solar system crosses this physical barrier, transitioning from repelling dust grains into solid, kilometer-wide boulders. We still do not have a complete mathematical explanation for how this happens. While the rocks struggle to form, a strict countdown begins. The massive disk of gas surrounding the young star is highly volatile. Within a few million years, the star's radiation will completely blow it away. This diagram compares the two leading theories. Left, the standard core accretion model, where a rocky center slowly gathers mass. Right, the disk instability model, where gas collapses under its own gravity. Core accretion takes too long. The gas dissipates before the core is heavy enough. Disk instability solves the time crunch, forming a planet directly before the radiation clears the disk. To understand which model reflects reality, astronomers look to the largest object in our solar system. Jupiter has over 300 times Earth's mass. Its massive atmosphere, defined by the Great Red Spot, required capturing an immense amount of gas. The sheer size of our gas giants proves that early planetary formation was a chaotic race to scavenge material from a rapidly dying disk. If a planet successfully navigates the dust barriers and the gas disk's time constraints, it must then survive the evolution of its host star. For Earth, that test began roughly 4 billion years ago. Stellar physics dictates that stars gradually grow brighter as they age. When life was first emerging, our young sun was 25 to 30% dimmer than the active, erupting star we observe today. Under that reduced solar output, Earth sat outside the temperature range for liquid water. Its surface should have been a solid, frozen sheet of ice. Yet the geologic record contains irrefutable evidence of ancient riverbeds and water-formed minerals from this exact era. Liquid oceans were abundant. This clash of physical sciences is the faint young sun paradox. Stellar physics predicts a frozen wasteland, while terrestrial geology proves a wet, flowing world. The resolution lies in the atmosphere. 4 billion years ago, the air was vastly different, containing extreme concentrations of greenhouse gases, primarily carbon dioxide and methane. This heavy chemical mixture operated as a massive thermal blanket. It aggressively trapped whatever faint heat the young sun provided, artificially elevating the planet's surface temperature above the freezing point. This specific, temporary atmospheric anomaly kept the oceans liquid long enough for complex chemistry to begin. It provided a narrow bridge of survival for early life. Zooming out from Earth, we measure our planetary arrangement against the rest of the Milky Way. For centuries, astronomers assumed our layout was the universal standard. Small, rocky planets tightly orbiting the star, with massive gas giants maintaining a wide perimeter. That assumption held until the launch of the Kepler and TESS space telescopes, which systematically surveyed the galaxy and cataloged thousands of distant exoplanetary systems. This visualization maps the distribution and size of discovered exoplanets. Our solar system fails to align with the average. The most common are super-Earths, large, rocky worlds. We also find hot Jupiters, massive gas giants orbiting close to their stars. Our system contains neither. The systemic architecture we use to define planetary formation is, in reality, an extreme statistical outlier. Earth's exact mass, its stable, circular orbit, and its capacity to maintain liquid water are rare outcomes born from specific, chaotic variables. We are not the inevitable result of a textbook equation. Our existence relies on surviving repelling dust grains, racing against dying gas clouds, and enduring faint, ancient stars. For centuries, astronomers looked up and assumed that what they could see was all there was. The glowing stars, the swirling gas, the bright dust. The assumption was that the mass of these visible, spinning structures accounted for the entirety of a galaxy's gravitational pull. This vector graph maps the orbital velocity of stars based on their distance from the galactic center. The laws of physics predict a downward curve. Stars further out should orbit slower, just as Pluto creeps along compared to Mercury. Instead, the data plots a flat line. The stars at the extreme outer edges continue to race at staggering, constant speeds. With velocities that high, the visible mass we are observing does not generate enough gravity to hold the system together. By the strict laws of orbital mechanics, a galaxy moving this fast should shred itself, flinging its outer stars off into the deep vacuum of space. Yet these spiral galaxies remain perfectly intact. The physical data indicates they are embedded inside a massive, invisible scaffolding, a dense halo of unseen mass providing the extra gravitational glue required to keep the stars from escaping. The first astrophysicist to document this missing mass was Fritz Zwicky in 1933. Zwicky turned his attention to the Coma cluster, a dense swarm of over 1,000 galaxies. Tracking the motion of individual galaxies within the cluster, he calculated they swarmed much too fast to be constrained by the gravity of visible light alone. The mathematics were sound, but the claim was so extreme that the astronomical community largely dismissed it. The telescopes of the 1930s simply lacked the optical precision necessary to verify velocity readings on such a massive scale. 40 years later, Vera Rubin utilized highly sensitive spectrographic instruments to track the rotation curves of dozens of individual spiral galaxies. Her equipment was measuring the exact redshift and blueshift of the rotating gas and stars, providing undeniable motion data. Rubin's results were definitive. Every single spiral galaxy she measured exhibited the exact same high-speed rotation at its outer edges. The discrepancy was not a rounding error or an isolated statistical fluke. The sheer volume of matching rotational data left no alternative. Physics had to accept that normal, visible matter was a minority component, and that an entirely invisible substance, termed dark matter, dominated the structure of the cosmos. We cannot observe dark matter directly, but we see its gravity manipulating the space around it. General relativity dictates that immense mass physically curves space-time itself. When light from a distant galaxy passes through one of these heavily curved regions, its path is bent and magnified, creating a distortion called gravitational lensing. By measuring the exact angle and severity of those light distortions, astrophysicists work backward. They calculate the exact mass and position of the invisible object required to bend the light, allowing them to draw precise maths of dark matter concentrations. The definitive physical proof of this substance comes from the bullet cluster. This system is the aftermath of two massive galaxy clusters slamming into each other at millions of miles per hour, an impact that permanently separated the normal matter from the dark matter. The X-ray data reveals normal matter. The hot gas clouds, in pink, smash together in the center, generating intense heat and decelerating. But the lensing data, in blue, shows the dark matter halos passed straight through without slowing down, experiencing zero friction. This proves dark matter is a distinct, tangible material. It does not interact with electromagnetism or friction, yet it exerts absolute gravitational dominance over the galaxies trapped within it. While dark matter dictates the localized structure of galaxies and clusters, the universe as a whole is governed by a completely different dynamic. Space itself is expanding. Throughout the late 1990s, the operating assumption among cosmologists was straightforward. The collective gravitational pull of all the normal and dark matter should eventually apply the brakes, slowing the rate of cosmic expansion over time. By tracking the redshift of distant supernovae, researchers discovered the exact opposite. The expansion of the universe is not slowing down, it is accelerating, pushing galaxies apart faster and faster every second. This diagram illustrates the accelerating expansion, driven by dark energy, a repulsive field permeating the vacuum. It is a property of space itself, actively generating new space and pushing matter apart. As the universe expands, more dark energy comes into existence, continuously increasing the expansion rate. The cosmos is locked in a tug-of-war. Dark matter's gravity works to pull structures together, while the repulsive force of dark energy aggressively tears the universe apart. When you tally the cosmic ledger, every star, planet, dust cloud, and atom humanity has ever observed makes up less than 5% of the total energy density of the universe. The remaining 95%, the dark matter anchoring the galaxies and the dark energy pushing them away, forms the dark sector. Understanding this unseen majority is the primary objective of modern astrophysics. Up to this point, our knowledge has relied heavily on legacy observatories like the Hubble Space Telescope, staring deep into the cosmic past to catch isolated glimpses of these anomalies at work. But capturing isolated phenomena is no longer enough. The current scientific mandate is to actively map the entire unseen architecture of the cosmos, constructing a comprehensive atlas of the dark sector. To execute this, engineers are building precision instruments like the European Space Agency's Euclid and NASA's Nancy Grace Roman space telescopes. These missions are designed specifically to survey the distribution of galaxies across vast swaths of the sky. By charting the cosmic web through billions of years of history, these observatories will measure exactly how the distribution of dark matter has changed and pinpoint the precise rate at which dark energy is currently overpowering it. The ultimate fate of the universe, whether it ends in a slow freeze or a violent rip, depends entirely on the physics of the dark sector. Humanity is racing to map this invisible scaffolding before the accelerating expansion pulls the evidence forever out of reach. Humans have spent centuries charting the night sky. We track orbital paths, measure background radiation, and trace the cosmos back to the Big Bang. We have built what appears to be a comprehensive map of reality. That map relies on a framework called the Lambda CDM model. It acts as a mathematical rulebook, predicting an orderly universe scattered evenly with stars and countless spiral galaxies, plus the basic chemical building blocks required for life. According to those rules, the Milky Way alone should be teeming with biology. Yet when we point our instruments outward and listen, we find nothing. the great expanse is silent. This persistent silence forces a confrontation with our baseline assumptions. If the math predicts a crowded galaxy and we find a void, the error likely lies in our definition of how the universe is built. Only rarely does anything interrupt that cosmic silence. On a summer night in 1977, a radio telescope in Ohio picked up a powerful 72-second burst of energy coming from the direction of Sagittarius. The data matched the narrow-band profile expected from an intentional interstellar transmission. Despite decades of continuous scanning, the signal never repeated. In 2017, a small, dark object named Oumuamua passed through our solar system. As it left, it accelerated away from the sun. It displayed no cometary tail or outgassing that could explain this burst of speed. Isolated events like the wow signal and the acceleration of Oumuamua suggest that the universe contains interactions that our current astrophysics cannot yet describe. The discrepancies extend beyond isolated objects to the very structure of the cosmos. Scientists rely on the cosmological principle, the assumption that on a large scale, the universe looks roughly the same in every direction. The test of this principle is the cosmic microwave background, or CMB. It is the faint thermal afterglow of the Big Bang, mapping the earliest radiation in existence. This map shows the largest temperature patterns in the observable universe. Instead of random distribution, they align along a single axis, pointing directly toward the ecliptic plane of our own solar system. If an impossible alignment were the only anomaly, it might be dismissed as a statistical fluke. But the CMB map holds another deviation. This underdensity is the Eridanus supervoid. It is a region of space nearly 1 billion light-years across that is almost entirely empty of matter. In a uniform universe, a void of this scale is not expected to exist. To accurately model reality, we must measure exactly how fast the universe is expanding. Astronomers observe the late universe with instruments like the Hubble Space Telescope, tracking distant supernovae to calculate how quickly they move away from us. This chart shows the late universe expansion rate consistently at a speed of 73 kilometers per second per megaparsec. A second method, analyzing the early universe's thermal afterglow, predicts what the expansion rate should be today. That calculation yields just 67 kilometers per second. The gap between 67 and 73 is the Hubble tension. These two numbers describe the exact same physical property, yet they do not meet. Our observational tools are highly advanced, repeated across multiple independent studies. This is not an instrumental error. To explain this gap, we must consider that either our understanding of dark energy is wrong, or there is a fundamental force of physics acting on the entire universe that we simply have not yet discovered. The math is in direct conflict, indicating that the most successful model in human history is missing a component at its core. Because we do not truly understand dark energy or the rate of cosmic expansion, the final chapter of the universe's history remains unwritten. There are several possibilities. If gravity eventually overcomes expansion, it pulls reality back in on itself, ending in a concentrated collapse called the Big Crunch. If the current expansion holds steady, the cosmos will stretch out until galaxies drift apart and stars exhaust their fuel, resulting in the dark stillness of heat death. If dark energy increases over time, the expansion accelerates until the fabric of space tears matter apart, shredding stars and atoms in a big rip. Returning to the scale of our own night sky, the weight of these unsolved problems can feel significant. Yet the breakdown of a model is a requirement for progress. When equations fail to describe reality, they force the development of a more accurate framework. These anomalies provide the coordinates for future research. They identify the exact points where our current laws break down, showing us where we must look for the answers we are missing. The most significant discoveries emerge from the data we cannot explain. The universe is behaving in ways that do not fit our current rules, which means we are approaching a different way of seeing the cosmos.